Swayam Prabha. Digital India. Educated India.
Well, today we will not open up any new topic. We'll just discuss about moving frame only. So that means that we did a little bit of statics to start with, right? All equilibrium equations, and 2D, 3D, and then we did a lot of other virtual work principles. And then we came to the dynamics part. Then we had the description of, we talked about kinematics, we talked about the kinematics, how to describe the motion of a particle. And so that means that how we define, the position vector, how we define the velocity, how we can find acceleration in various frames. So to start with, we had different frames. Simple one is the curvilinear coordinates. Then obviously, basically before that we had Cartesian, then curvilinear, and then we had polar, we have 2D, then we also had 3D spherical systems, and that was about the coordinate systems. After that, we, of late in the last 1.5 weeks, we have been discussing about the moving frames. All are important topics, okay? So there's nothing which is unimportant, because unless you know how to do the force analysis, how to draw the free body diagram, you cannot go to the dynamics. Similarly, unless you can describe the motion of a particle, so you cannot go to the kinematics of rigid body. Then we have connected bodies, and of late we have been discussing the moving frames, very an important topic. Okay, not only from our own rigid body point of view, but if some of you are interested in the mechatronics, so where you have several links and several motions, several degrees of freedom. So if you want to describe that, both from the position point of view, both from velocity, accelerations point of view, so you do require. So all these things are very important. So that way, this engineering mechanics is really, they call it difficult or call it a very interesting thing, that right from day one lecture to all the way to 3-dimensional gyro mechatronics, gyrodynamics. So all these things are very much related. So you have to be good at each and every stage. Okay. So obviously, starting from equilibrium up to some little bit about the moving frames. Okay. So I hope you are getting some picture of the moving frames. What is the relationship between the observations made in the moving frame, either translating and rotating or both, and how it is related to the velocity and accelerations in the observations made in the fixed frame. In fact, both can be moving also. It's not necessary that one has to be fixed and one has to be moving. So that's what we are doing. In fact, even yesterday we were saying that the ones which we talked about, the accelerations here, the centripetal acceleration, tangential accelerations, and Coriolis components, how you can see them in the polar coordinates also, how each term is related to that. In fact, yeah, interestingly, I'll come to that. So I'm just doing a few examples. So now I wanted to start a new topic. Probably I won't do that. So the next topic is the rigid body. Okay, so we'll start the kinematics of rigid body as soon as you come back after the exams. But if I start a new topic, and then probably you cannot concentrate really well. So I'll go very light today. So if you have any questions, you can always ask me. But however, I try to explain the concepts of moving frames. I illustrated with some examples today, so I'll continue with a few more examples, and then I'll also relate it to other coordinate systems. So another simple example here. And moving, in particular, translating is not a problem. And in particular, we have the rotating frames. So we did some examples yesterday. I'll continue with one more example. I will just only do a few examples today, not very much new theory. So we have a disk here. And the point P here. So there's a disk here, and in which we have a slot here, a straight slot. At this instant, the slot is vertical, and then there's a point P here, a bead which is moving in the slot. So the data is that at this moment, the point P is a distance of 8 meters vertically and 6 meters horizontal distance from the origin here. So some of this numerical data are okay. I hope you have noted down. So the angular velocity is 5 radians per second, and angular acceleration is 3 radians counterclockwise. And then this point P, has a velocity with respect to the disk. And let's say we have a big xy, which is the fixed frame, and a small xy. And small xy is attached to okay. So this is all the data we have here. So what we have important is that we had to set up this small xy, which is attached to the disk. So you can take xy in any directions, but what we, for simplicity, at this instant, we let it coincide with big xy, okay, at this instant, so that ij, small ij are coinciding with big ij, okay, but however small ij has a rotational component. Okay, so if this is a very straightforward problem, however, I have taken it just for the sake of illustration. So what we have here is that okay, so the position vector of this with small xy is very simply 6i plus 8j. So this is the various things. So omega is given there, and so we have omega 5k, and alpha is tk. So we are putting everything in terms of vectors ijk. So if you want to find out the velocity of this one, so the velocity that's given here is 4 meters per second of p is going in the slot. So what we have here is that then, so the velocity of p with respect to the big xy frame, fixed frame, is nothing but velocity as observed in the small xy frame plus omega cross r here. Okay. So r is observed in small xy. Even you can also write it with big xy, but however, this is the correction term. So what we have here is very simply, so this vxy is given as 24i, and this is 5k cross r is 6i plus k. Okay, so simply then you can do that. So it's minus. So this is the velocity. Okay, simple. And similarly, we can also do the acceleration. So we just faithfully follow the acceleration with respect to the fixed frame is nothing but acceleration as observed in small xy frame plus, simply since I could have written to omega cross r, but otherwise I can also write it as omega square r, and we have alpha. If you want, we can write alpha k cross r, and finally we have so this is the complete expression for the acceleration. So just as example, so since here, I'll just put all these terms. So the acceleration of the point P is 30 with respect to the, so it's 30J, right? It's going up acceleration. And then we have 5 square. Rxy is simply 6I plus 8J. And then this is 3K cross R again. The last term, Coriolis, is 5K.
Sir,
Yeah.
in the left side, you wrote 24I cap plus pi k cap into that cross product, but you gave wrong answer in the minus 40I cap and such, sir.
Is it minus 40?
It's 24J cap.
V of capital X, capital Y, sir.
Minus 40I, 54J. So this is not right, right? Yeah. Okay, okay. I'm sorry. Yeah, that's right. That's right. Yeah, that's right. Thank you. Yeah, good. Thanks. So continuing here, so we have 5K cap 24J. So this is 24J is the velocity. Yeah, 24. So this is the velocity with respect to the moving frame, rotating frame, and this is the omega. So you can combine all these things. So interestingly, so I'll just give it this one, minus 414 I 242. Okay, so that's that part. So I just put down, this is a simple problem. So I just put down the numerical values. If you need to solve something numerical, so this is what you have to put down. So interestingly, I would like to throw something for your imagination. Yesterday, we were talking with giving a very elaborate explanation for Coriolis component. When, okay, so we gave Coriolis explanation for that, wherein we have taken a slot here, and so we have taken this slot and a radial slot we have taken, a radial rod, we have taken rod, but here it's equally applicable to the slot. So there we said that the Coriolis component comes as a factor of 2. So 1, because the V is changing. So this is V. So this is one component because the sliding velocity has changed. The other one we said is because the velocity here, omega r, so this is the one we said that the tangential velocity here, because of omega, how it is affected by the velocity of V here. So you have V, and this is so the position P has changed to P prime by a magnitude delta R, in which case R omega has become R plus delta R omega. So that gave rise to a change in the velocity delta r omega and divided by delta t. So that is nothing but v omega. So both of them turned out to be v omega, right? So now can you apply that here? So here the slot is perpendicular, not really radial. So here we gave this explanation. So in which case, what happens? This is, I'll leave it to you. You have to think. So what I'm asking is that in this case of perpendicular slot, so what is that which we have here? We have the first one, for example, is a V, and V is changing. V is changing by a certain thing, right? V changing by a certain delta theta, and this becomes V delta theta. Okay. And what is the other one? The other one is also about R omega. So, but this is B, and then there's also an R omega, which is going to change, okay, by a certain angle, right? So, but then this totally, if you look, actually it is a combination. So the total velocity of the particle is not only r omega plus v. So both of them are tangential, and this essentially will lead to a centripetal acceleration. So it's actually, if you look at that, okay, so this is, so but then will it change? So it is not, so the particle is going from P to P prime, and the same here. Here there is no change. Here there is no change in the r omega, as we have seen here, r plus delta r omega, because delta r is also in the same direction as in the vertical direction. So where is that? How do you explain this Coriolis component here? Because both are r omega and v are both in the same direction. Okay, so this is because this is coming because again an interaction, but however you can do it. So the total velocity here is v plus r omega, and if you look at the centripetal acceleration, so this is by r. So this is the centripetal acceleration. Okay, so in this centripetal acceleration, so we have several things. So we have v squared by r, and so can you understand here what is happening here? So there are several things that are taking place here. One is this is the v square by r because of the centripetal acceleration. So this is the one which is coming as Coriolis. So think about this. So I want you to think about what happens in this kind of situation. And then you have another r omega square. So this and this get combined. Okay. So anyway, I'll leave it to you as a food for thought. There's also another thing, very interestingly, is that the formula which you have derived, polar coordinate accelerations, I said that they're quite similar, but the polar coordinates itself in 2D, so polar coordinate equation from moving coordinate. So can we derive it? You understand? So now that we know how to analyze it in the moving coordinates, so can we derive the equation which we had? Okay, if you recall, so in fact we have, this is what I'm trying to say is that, so if you can understand both ways, so how to interpret polar from moving coordinates, or how to relate polar equation, can we derive polar equations from the moving coordinates itself? Okay, so let's see, so that we'll have more hold on this one. So in polar coordinates, so what it is that we have point here which is given by r, right? And what are the coordinates here? So if you look at the coordinates here, so the coordinates are er and e theta. Instead of small xy, so I'm saying that er and e theta. So this er e theta unit vectors representing polar coordinates. So what is happening? So its origin is right here, but then as you go from this point to this point, like this one, so you can see that this coordinates, er e theta coordinate system, is rotating by rotating, right? So it's, their directions are not fixed. So this coordinate system is rotating at a omega of what? Theta dot, right? As well as alpha of theta double dot, right? So from this point of view, so can we derive the velocity and accelerations from our understanding of the rotating coordinate system? Or how do we do that? So how we do it is exactly apply the same formula. Exactly the same formula we can apply is what? So for example, if you want the velocity, the big xy, so this is velocity in the rotating system. Instead of small xy, I'll say simply a relative term. So I don't write x, y, or theta. Now we are quite comfortable. So the relative to the moving coordinate system. So that's what usually the convention. So rel means relative to the moving coordinate system. And then this is the other omega cross r. Okay. So what is this one? So what is this? As far as the particle is concerned, particle is just moving along ER, right? So it is always in the direction of ER. So what is its velocity? So its velocity is r dot only. So always it is, the ER is moving in, rotating in such a manner that P is always along ER. So that means that the particle P is only having a velocity of r dot, and as a vector quantity, I'll put it as ER also. So as far as the rotating coordinate system is concerned, the particle P is just moving along R, nothing more. Okay, so what about this one here? So omega is theta dot k, and what is the position vector here? Position vector is R, ER. Okay, so this is this, and so R dot ER plus what is this? K cross ER is nothing but E theta. So that means that, see, this is another way of doing that polar coordinates. So we did it in our own way, but then if you want to do that from the knowledge of rotating coordinate system, so you get the same formula, right? Okay, you can go even one step more and get A. So if you want to get the acceleration here, what is that which we need? So we need acceleration in the relative term minus omega square r plus so we write del. So this is from the moving coordinate system. So what is this? The acceleration of the particle in the rotating frame. So what is happening in the rotating? What is the particle doing? So the particle is always moving along ER, and its acceleration is velocity is r dot and its acceleration is r double dot. So this is nothing but r double dot ER. Okay, and this is theta dot square. And what is r? R is nothing but vector. So r ER. Right? Okay. So now here coming to alpha k. So alpha is theta double dot and k cross what is r? So it is r ER plus theta dot k cross relative velocity is r dot ER. Okay. So this is from that. So let's continue this one. And so the total acceleration now is r double dot. In fact, I can combine this one. ER. So this is the first two terms, and then this is k ER is nothing but E theta. So you have r theta double dot, and then k ER again is theta, and that is 2r dot theta. See, it is so nicely. Now we can derive the polar coordinate velocity and accelerations from the knowledge of the rotating coordinate system. As long as we realize that this ER, E theta, basic unit vectors, are not constant in space, but then they are actually rotating at an angular velocity of theta dot and an angular acceleration of theta double dot. So that way all these various approaches are one and the same. You can also do that. In fact, the same thing can be applied once more. I will not do it, but I will just indicate that yes, this can be applied to 3 dimensions also. So how do we, what is that all required? So this can be applied to spherical coordinates. I will just indicate how you can apply yeah. So this is So here XYZ is fixed coordinate system. So I just want you to get what is the rotational part. So if you can understand rotational part. So this is XYZ, and the coordinate system for spherical coordinates are ER, and this is theta. Okay, so this is R, and so ER is in this direction. Theta here is, and this is the phi here. Okay, so this is what R theta phi systems are. So I'll just indicate what are the things. So the things here are the position vector here is nothing but, just put it as big R, because this is the position vector. Okay, so and then just like we have done, so we call it as relative to the rotating frame is what is simply R dot R. So wherever this particle P moves, so the coordinates do change, but all the time ER is along the OP direction. So always the particle P moves along ER only. So I want you to understand only one thing here, and then you have relative acceleration also is nothing but R double dot ER. So once you have this, so only thing that is required here, so what is omega? If you can recognize what is omega, so the rest of it just falls in place. Everything falls in place. Only you have everything. So if you want to know what is omega, so what is omega here? So omega, the rotation, this ER, E theta, E phi are changing their directions because of what? Because, for example, if there is a increase in R, it hardly matters, the directions won't change. So the directions will change only because the theta is changing because of theta dot and because of phi. The change in phi, you call it as phi dot or phi double dot. So omega is dependent on theta dot and phi dot. So interestingly, if I change phi, so what is the angular velocity direction? So if the point P is moving like this, which is similar to this one, so if phi is changing, so if you have a phi dot and if you want to represent it as a vector, so what is the vectorial direction you can give it? That component. Okay, so the phi dot is in which direction? Phi dot. So it has a phi dot component, and phi dot, if you rotate P in such a direction that phi changes without changing theta, so that will be in the direction of Z, right? Because it is rotating in the horizontal plane everywhere. Even here it is moving in the horizontal plane. So its vectorial direction is A, right? So this is, and this is about phi dot. And we also said that these angular velocities are vectors. You can definitely do addition, any vector addition. So this angular velocity, this is only one component. There's also another component here, theta dot. So theta dot is the component angular velocity. So we keep keeping phi and we are keeping theta. Okay. So if you are changing theta by theta dot, okay, so then what is its vectorial direction? Can we tell? So that means that this point mu is moving along this arc, right? So what is the direction? Then what is the direction of this theta dot? Okay, it should be perpendicular to this plane. So this is the plane. This is the plane, and then the vector perpendicular to this plane is nothing but your E phi. Okay, so this is in the direction, right? So that's it. So everything is given. So this is a position vector. This is a velocity relative to that, to the rotating coordinate system. This is acceleration rotating, and this is the angular velocity of the rotating system. So you can definitely find out the velocity is nothing but VREL. So I will not do anything here. So this is omega is a combination vector here, and then this is okay. So that's all. So you substitute this omega in this, and what else you have to do? You have a k here. So this k need to be transformed into r theta phi, so that the whole equation in terms of is r theta phi. Okay, and you can do one more step. You can get the accelerations also. So I will not go into that long algebra, but what I said is that so all these coordinate system can be explained one from the other. So there is no variance. Okay, so we are not at variance with any of these things. So one other small example, I'll just take it up. We have, so interestingly, a very small example, I think it's also one part of tutorial, is let's just another example here. So let us say this is horizontal. We have two circles here, and then there is one car going along this circle, and another car. So these are just executing a circular motion here. Okay, so what it is that, so somebody who is sitting in this car A, assume that he knows only the forward direction, he knows left, he knows right. So apart from that, he doesn't know anything. So if he is observing this V here, so what is that he finds the relative velocity? I mean, as far as this is concerned, what is that he finds it as? And velocity maybe as well as acceleration. So let us assume that at the instant, let us say that A is here, and at this instant, so B is moving in this direction. Let us say velocity. So we would like to understand. So we would like to, you want to find velocity of B to A. So there is a rotating frame. There is a with respect to its front and side. So this is, so that means that anywhere here, for example, if here is here, So if you have an origin here, this one, and this not only its origin is moving, but also it is rotating. So that means that if you want to find out velocity of B with respect to A, so that means that you have to relate these quantities using our relationship. So for example, here, if you want to find out VB, so it is nothing but the velocity of O prime of A and velocity of B with respect to A and okay. So this is because here this is the O prime, so this is O, let us say. So this O prime itself is having a certain velocity, so that is what you need to put here, O prime. Okay. So for example, in this, I'll just give you a quick relationship. So we can put this one VB at this instant. So at the instant when theta is equal to 0 and phi is 90 degrees. So that means it's here, right? So what we know here, so VB in an absolute sense, it is U I, okay, let's put it that way, and velocity of O prime. So the velocity of O prime here, if it is at this point, is nothing but Uj, right? That's V O prime, and velocity of B with respect to A. So this is what we want to find. And the correction term here, omega cross RBA, so it is nothing but omega K cross B with respect to A is nothing but, say, if it is radius is R, so it is nothing but Ri. So this is the relationship between the velocities. And if you want to find how much is this is omega R K cross Ij omega R. So if you want to find out the velocity of B as observed in its own rotating frame, is nothing but Ui minus Uj minus. Okay. So this is to find the velocity of B as observed in the moving and rotating frame is given by this vectorial component form, right? So this is how you can go from fixed to rotating frame. Not always from rotating frame to always rotating frame observation to fixed frame, but here some of them are fixed and we need to find out what will be. So for example, if he has a radar fixed on this one, so how it has to be rotated so that this can be tracked. So that's how you can find out here. I think I'll stop here.